In B3, this is about beta plus positron decay. In a beta plus decay, a positron is emitted along with a neutrino and a gamma ray photon. Although the energy spectrum for the gamma rays involved is discrete, the energy spectrum for the positron is continuous. State the difference between a discrete energy spectrum and a continuous energy spectrum. With a continuous energy spectrum, the energy can be any value. Energy can take on any value, but with discrete, it takes on a specific value. So, to explain how the existence of the neutrino accounts for the continuous nature of the positron energy spectrum. Well, the interesting thing, when they looked at radioactivity, they always found that the energy was discrete when they were looking at alpha particles, alpha 2 plus, and gamma rays. It was always discrete. But when they looked at your beta radiation, either your beta minus or your beta plus, this was continuous. It seemed to take on any value. And so the neutrinos actually found that the energy of the beta plus the neutrino, those two together equals a specific value, a discrete value, specific discrete amount. But these two just change. So obviously if the beta plus is large, this would be small, and these two change according to give a specific complete value addition of those two energies. Moving on to B, sodium 22, this is the mass number, is a radioactive isotope used in nuclear medicine that undergoes beta plus decay. The half-life of sodium 22 is 2.6 years. A sample of sodium 22 has an initial activity of 2.6 times 10 to the 9 Becquerel. So in defining this over here, firstly define the decay constant. For the decay constant, it's the probability of decay of a nucleon per unit time. So it's a probability of decay of a nucleus, and what's very important is of a nucleus per unit time. So calculate the decay constant of sodium 22. For that, we're going to use this formula over here. Your decay constant, this is the symbol used, the lambda. So if we want to work out the decay constant, we have the half-life. We are given the half-life is 2.6 years. So it's going to equal the log, the natural log of 2 divided by 2.6. So we can put that into our calculators. And we're going to have your natural log is given by this one over here. So it's ln of 2 divided by 2.6. And we get our value here. Now we are working to two specific figures here, two significant figures. So we're going to get 0.27. And that is going to be a year to the -1 value, because we're dividing here obviously by years. Then it says calculate the activity of the sample of sodium 22 after 8 years. Now in doing that, we're going to come here. Now we're actually going to use this formula over here, because this formula over here actually gives it to us. This lambda n0 you can write as A0, because that's the activity. The lambda times your number of particles gives you activity, and that would give you your initial activity when you have got your initial number of nuclei. So we're going to use A is equal to A0 E minus lambda T. Now, we can just put that straight in, obviously. So we have got our A0. We are told what our A0 is. It is 6.2 times 10 to the 9. And we multiply that by E. And we then say minus lambda. Lambda we saw is 0.27. And we're going to multiply that by 8. So bringing my calculator back again. And we're going to put that in, so it's going to be 6.2, my exponent, 9 times, now we need the E, and we're going to use this over here. We use this button over there. That gives me e to the x, and here I put in my minus. Now, probably a good idea to, well, this is fine actually, we don't need to put in brackets, I don't think. 0.27 times 8, that's all fine. Enter. Now we get here a long number here, but we only want to do two significant figures. So two significant figures would be 7, 2, and I've got 1, 2, 3, 4, 5, 6, 7, 8. So 7.2 times 10 to the 8. That would be my activity. So 7.2 times 10 to the 8 back wheel.